So we'll continue our discussion on baseband shaping. Purpose of this line coding or baseband shaping is to mitigate the demand for bandwidth corresponding to the data transmission rate, and also to mitigate the problem of inter-symbol interference that we shall discuss a while. So last day we are discussing about various formats. That is, we have discussed NRZ, RZ.
Excuse me, sir.
Yes.
The test is on Monday only, not today.
No, there is no test today.
So it is on Monday.
Yes, yeah, there will be one small test on Monday. I will announce, I will send a mail for that. Okay.
Okay, sir, thank you.
So now we have discussed about the spectrum of non-return zero unipolar format. So there are two aspects of the spectrum. One is the spectrum given rise to the occurrence or the statistics of the symbols 0 and 1. Now the symbol 0 and 1 is coded differently in different line coding format. So accordingly, that will create a component of the spectrum. And then another component is created by the pulse shape, that is VT. So both together we have computed this spectrum. So there is one component coming due to this RAN, and another component is coming due to the spectrum of the pulse shape. So together we have this SXF. Now the pulse shape in this case, of course, we have assumed to be rectangular in nature. We will see that this pulse shape also contribute to the inter-symbol interference significantly, and that also need to be manipulated further to reduce the inter-symbol interference. However, before that, we shall just discuss a little bit further about one or two more formats. So if we consider non-return zero polar format, in this case, the symbol is plus A and minus A. So the AK is either plus A and minus A. Assuming equiprobable occurrence of the symbols, we can easily write that for the symbol AK equal to A will be the probability of the symbol of occurrence of AK equal to minus A is equal to half. So therefore, for n equal to 0, that is if we take the expectation of AK square, so that will be A square by 2 plus A square by 2. equal to S square.
So,
Yes.
like I was offline for like few minutes. So like when is the next test, sir?
Next test will be on Monday. This Monday.
Oh,
This will be a small test. I will announce through an email. Okay, tonight that the test will be on this Monday. It will be half
like
an
we
hour.
were hoping for like a week's notice, so you could have some time to prepare. So like,
Okay, so you want it
Sir,
to
can you
be
shift it to next week?
Thursday,
it can be
No,
next
sir,
week,
next
but
week. Next week
like
only.
little bit of
next
notice
week.
we need because we have other tests coming up also.
So
Yes,
then
sir. Maybe Thursday or Friday could be better.
Yeah, if possible, like because otherwise it will cause a little bit of issues with other tests also.
Friday. Okay, I don't have any problem. So then Friday will be the test. Okay,
All right,
next Friday.
all right.
And for AK for n not equal to 0, that is in that case we have AK minus n. So that gives produces 4 combination. So those are accordingly we have, that is A into minus A, one combination. Basically 0 and 1. 0 and 1 can occur like 0 0, 0 1, 1 0, 1 1. Now if 0 is minus A and 1 is plus A, then so that way these symbols occurrence are there. Sorry. So the probability would be P AK corresponding to all these would be equal to, so expectation of again we if we assume equiprobable, so this will be plus 4 plus so this is equal to 0. So therefore RAN, the autocorrelation, RAN equal to a square for n equal to 0, 0 for n not equal to 0. So Vt is of course same as the unipolar case. So therefore SXF the spectrum would be a square. This is this statistical part is coming here, and then the spectrum of Vt, that is the spectrum of a rectangular pulse of duration Tb. Now, if we go to bipolar format, so bipolar
Sir?
format, yes,
Sir, how Vt is same as in the unipolar case?
no, because this is the same rectangular pulse we are using for, sorry. Unipolar is this one, okay, and bipolar is polar is this one, okay. So the basic Vt is same, this rectangular pulse. Now, rectangular pulse, this Vt is equal to here, this like this, okay, and then for 0 it is minus a. So minus a into Vt giving 0, and a into Vt giving 1. Okay, but here unipolar case, this 0 into Vt, here Vt is the same, Vt is same. Now 0 into Vt is giving 0, and a into Vt is giving 1. Yes. So that way the basic pulse shape is same rectangular type, and therefore the Fourier transform is that same sinks function having the time period of Tb.
Okay, sir.
Now for Energet bipolar format, of course, has 3 levels. Bipolar we have A minus A and 0. A0 and minus A. Again, assuming 0 and 1 as equiprobable, the probabilities are P, AK, equal to 0, equal to half. However, for 1 actually it is divided, because 1 this A is occurring in alternate fashion. So therefore, for 1 PAK equal to A would be 1/4, and PAK minus A is equal to 1/4. So this is together they are representing the probability of occurrence of 1 equal to half. Now therefore for n equal to 0, we take the expectation of AK square. So that would be a square into P AK equal to A plus 0 square plus minus A square plus 0 square into P AK equal to 0 plus minus A square into P AK equal to minus A. So this is equal to, again, if we add, that will be A square by 2 and for n equal to 1, AK minus 1 AK. We are doing here for only for n equal to 1. For n not equal to 0 case, actually most all other cases will be 0. Only for n equal to 1, there will be some non-zero term. So that's why n equal to 0, 1 is estimated separately. Four possible forms, that is 0, 0, 0, 1, 1, 0, and 1, 1. So all these are involving 0. So therefore, AK minus 1 would give, those are involving 0 will produce this multiplication 0. Only this as 1. So this will have plus A and minus A. So this will be equal to minus A square. So therefore, expectation of AK minus 1 would be 3 into 0 into 1, 4 plus minus A square into 1, 4. So this is equal to minus A square by 4. So for n greater than 1, AK minus n equal to 0. So therefore, autocorrelation RAN equal to A square by 2 for n equal to 0 minus A square by 4 for n equal to plus minus 1, 0 otherwise. Now then SXF would be equal to corresponding to this. First term is a square by 2. So if we take the spectrum of Vt common, then this will be a square by 2 minus a square by 4 exponential of twice pi f dV, that is for +1, and for -1 exponential of minus j twice pi f dV. So this is equal to a square dV by 2 sin square f dV 1 minus cosine of twice pi f dV. This can be written also in terms of two products. Sorry, sin square f dV and a sine square term, sine square pi f dV. Because of this sine square extra term here, the this will shift the spectrum towards from the DC part. So DC part will be nullified because of this sine square term. So if we plot the spectrum,
Sir, wouldn't there be also a multiple of 2 when we convert?
where?
When we convert 1 minus cos theta into sine square theta by 2, there should be a factor of 2 as well. No?
There would be a 2 factor, so these 2 will go. Okay. Yes, thank you. So now if we plot it, this plot, we can plot it in normalized instead of f frequency. We are normalized with dB. So we plot with respect to f dB, and so we are plotting only one half of the spectrum, the other half is of course there. So for NRZ polar, there are two parts. One is a delta function. So there will be a delta function here. And then that sorry. Because of the square, basically it is sin square. So that's why there is no negative term. Only positive terms will be there. And also the main lobe versus side lobe ratio generally around 13 dB. So that ratio will also improve because of the square term. oh, sorry, I think this is for a different one. I have to. This is NRZ polar. For NRZ unipolar, the delta function, and there will be another one here somewhere from. So this is these two together will give NRZ unipolar. This is polar, and the spectrum, DC spectrum, will be nullified in case of bipolar. For Manchester, of course, we have not computed. For Manchester, this will be further shifted. So this basically the significance of the bit definition. Now we shall see that what would be the significance of VT, that is pulse shaping. All these cases, all these spectrums corresponds to the spectrum of a rectangular So the problem of rectangular pulse shape is that actually we cannot, like that it will carry on. So we cannot make it truly band limited, because truly band limited, ideal band limitation would be like a square band, which can be separated one from another. But for that, then the inverse transform of that would be a sinc function in the time domain. So that is the basic idea of pulse shaping. So because our initial design of the VT was a rectangular pulse that could be easily generated from square wave oscillator. So, however, it contributes badly to the spectral behavior. Now, to make the spectrum more or less square, if we want ideal square, so then we have, of course, have a sinc pulse shape. thinking in the complementary way. Designing a pulse shape for VT to achieve an ideal band limitation. We require a sync waveform to be generated in the time domain. Which is again not an easy task, because generally we can shape this pulse. Suppose we have generated from an oscillator a square wave, then we want to shape the pulse. And to give the shape of the pulse, we have to pass through a filter. So the problem is now becomes to design a filter which will generate this shape of pulse. Now, to generate a sync waveform like pulse, the frequency response of that filter has to be like a ideal rectangle, which is again cannot be designed by physical component. So therefore there some trade-offs need to be made. So this is the idea of reducing intersymbol interference through VT. This is usually approximated by a practical pulse shaping filter. So, so this requires, for this purpose, let us introduce a parameter named as intersymbol interference, or in short, this is known as ISI popularly. So to do that, we will write the time domain equation of the pulse amplitude modulated signal. And evaluate the effect of VT. The discrete pulse amplitude modulated signal is given by xt equal to k equal to minus infinity to plus infinity ak bt minus, so basic shape is bt. Now it is modulated by ak, that is the symbol. So the amplitude is modulated by ak. So vt is the basic pulse. So vt is time shifted as an integer multiple of tv. So tv is coming from the bit rate, that is RB. If RB is the bit rate, the time period for each bit is 1 by RB. So correspondingly, so vt is shifted and multiplied by ak, and those are summed up together to give a continuous signal at. At the receiver, of course, we will have several things. So like the receiver, again, there will be shaping, pulse shaping filters will be there. First, there will be a band pass filter to reduce the random noise. At the output side, usually there are several stage of filters. For noise rejection, and pulse shaping. Let us take that effect as a scale factor with respect to AK. Assuming these filters ideally give rise to a scale factor. Practically, there will be other terms, phase term will also come, but those considerations will make it much more complicated. So ideally give rise, so we will assume that give rise to a scale factor. Yt is equal to a scaled version of the desired weighted pulse waveform, the shifted pulse waveform. So mu is the scale factor. Pt is normalized. Again, the pulse waveform Pt is normalized such that P0 equal to 1. Now, this is the continuous Yt spread over minus infinity to plus infinity. So to get the symbols at every TB, we have to sample it at every TB. Why we have defined like a continuous signal xt and yt? Because it is assumed that we could not generate a pulse waveform which is time limited. Okay. And if we want to generate a pulse waveform in the time limited, then that in the frequency domain that becomes infinite. So because time frequency are basically two complementary domains. So therefore we will take an intermediate way. So we assume in effect if we have a pulse waveform which is basically due to the transmission or due to our original pulse waveform generation procedure, that pulse generator and the corresponding pulse shaping filters, the energy is spread. For any filter, actually, we cannot assume that the energy is limited in a particular time. So the energy will be attenuated over time and frequency of certain pulse, but its effect will be there. So therefore, to get that effect into account, we are taking xt and yt constant. So that means for any, say for p equal to 1, so there is a for p1, p or pt1 or t equal to t0, corresponding to say k equal to 0 pt. Okay. So there will be an effect of all other pulses, those has been sent for other time durations. Of course, here there is one question comes whether why we did not enforce causality. So okay. So PT is so that is not enforced. We have assumed that that is spread corresponding to all k. We have the contributions. Now the sampled version, to see the sampled version, sample version of yt is given by yti at the ith sample. Mu equal to minus k equal to minus infinity to plus infinity summation ak p t would be replaced because it's a sample version and we are sampling at an at the bit rate. So therefore that will be I into TB minus KTB. A lot of lightning. So that would be mu into AI, because we want the ith sample. So this is basically mu into AI. So this for k equal to I, it will come as mu into AI. And the rest for k not equal to I, minus infinity to plus infinity ak p ITB minus KTB. So this is, so therefore ideally it should happen that we should have only mu into AI. But this term is coming due to the effect of all transmitted bits on the ith bit. So this is known as inter-symbol interference. Now, here again, Nyquist come into picture. So, just like for all other sampling, Nyquist has contributed enormously. So, for this also, Nyquist gave a criterion. So, Nyquist proposed a criterion. There are two criterion actually, 2 or 3 criterions. So we will take just one. Nyquist criterion for distortionless baseband transmission. Now, after this, we will discuss about carrier band transmission, where basically we shift this band to a higher band to accommodate many basebands into one carrier band. So that we shall discuss later, but usually that is done for power transmission from one place to another place. But for very short transmissions from device to device, or maybe within the device, we can use this baseband transmission itself. No carrier modulation is necessary. So Nyquist criterion for distortion baseband transmission is based on the specification of transmitting and receiving filter. So transmitting filter is required to give rise a desired shape, and receiving filter is to extract that shape. So as to reconstruct data sequence. So Yt is determined by, as from the expression, that Yt is determined by solely Ak and Pt, because mu is independent of K, though practical cases mu to some extent depends on K, but here we have assumed mu to be independent of K. Yt is mainly determined by Ak and Pt. So to make the sampled Yt, to make the sampled YT, that is YTI, to be free from ISI. It required that the ith pulse, that is PITB minus KTB, is equal to 1 for I equal to K, for I not equal to K. So that means there is it will be sampled in such a manner that the contributions of the non-ith samples will not come into picture. Then YTI becomes simply a scaled version of mu AI. In the frequency domain, if we interpret it in the frequency domain, so PF equal to, or this, let us make it P delta F, because here it is becoming 1 for I equal to K. Other terms it is 0, equal to RB. RB is 1 by TB. Sigma n equal to minus infinity to plus infinity. F minus n into RB. So because RB is in the unit of inverse time, so it can be direct interpreted in terms of frequency. In terms of PF, sorry, this is capital PF. P delta F is Fourier transform of the sampled values of PT. So PF is the Fourier transform of PT, whereas P delta F is the Fourier transform of the sampled version of PT. So P delta F can be written as the Fourier transform of PT. Again, PT is a summation of the contribution coming from MTB and the all other waveforms, all other samples. This then we have exponential of that Fourier transform term, twice by ft dt. Now if m equal to I minus k, then I equal to k gives m equal to 0. So in that case, we can write p delta f equal to minus infinity to plus infinity p0 delta t exponential of minus j twice by ft dt. So that is equal to p0. That is equal to 1. I think p0 is equal to 1. P delta f therefore can be written as RB into that P into F minus N RB, that is equal to 1, or sigma n equal to minus infinity to plus infinity. One by RB is equal to TB. So if we define B a band, from minus B0 to B0 to cover RB, that is B0 equal to RB by 2. PF can be written in terms of B0, 1 by 2 B0. The rectangle of F by 2 B0. A rectangle function with width of 2 B0. So in that case, if we do that, this is the ideal case. So PT will be, the ideal PT will be then is the sinc waveform twice by P0 T divided by twice by B0 T, sinc of 2 B0 T. So this is the ideal case. Of course, this is not possible in practical situations. We shall discuss next day some practical filters.